May I begin?
Oui, ça va, la salle elle est en attente de votre intervention.
Super. All right, well, I'll be speaking in English and, of course, available to answer questions in French if necessary. Unfortunately, not in Italian. I apologize. So Fabrice and I were mandated to analyze GPS data collected during the Leman EVEX project. The objective of our work was to use all the data points collected to describe how Alpine ibex use land and also to describe the types of land they use. Today, I'm only going to be focusing on how they use the land, which corresponds to the first 5 chapters of the report we wrote for this project. I'll start by telling you a little bit about the data. So the data we collected came from 7 sources, which we pulled together to build a database with over 300,000 data points, which are shown on this map, and corresponding to 178 individuals and a whole bunch of CSV files and a lot of communication to make sure the data was clean and valid before we carried out the analysis. So I'm going to dive right into our results. One important measure that we used was to calculate the area used by each individual, also known as the home range. We used the kernel method to determine these areas for each individual. For example, on this map, we're showing the outline of Alpes-Maritimes Park, and in blue, the home ranges of the males, and in red, the home ranges of the females. We use these areas to define colonies of individuals who are close together. When we compared the size of the home ranges, we noticed that male home ranges are almost twice as big as that of females. When we look at the size of the home range for 10-day periods throughout the year, we notice that the home ranges are largest during the summer months and also show the most variability during these months. By using the closest individuals, we group them by pairs and group those pairs together, and then group these pairs of pairs together. We create this graph known as a dendrogram on the lower right. Each colored point in the bottom of the graph represents an individual. And the individuals who are closest have close paths on the graph. Individuals who are very far apart are symbolized by a long path. Using a statistical criteria, we choose to cut this graph, cut this tree into 4 groups. We call these groups colonies. Using all the points for all the individuals in each colony, we aggregate these points, and we recalculate the home range, this time not of an individual, but that of the whole colony. The home ranges of these colonies, the 4 colonies, are presented on this map. We were interested to see if there was any movement between colonies during the observation period. We found that 99% of data points were within the boundaries of the colony's home range. The few excursions we found outside the colonies were never very far away and never very close to other colonies. These excursions occurred mainly during the rutting period in November, December. The second most important parameter we looked at was distance. Typically using the distance traveled midday. So in this figure, we're looking at median, average, and maximum distance traveled for all the individuals. We find that most individuals travel less than 1 or 2 kilometers in a day. Maximum distance is around 10 times that of the average distance and can be as high as 40 kilometers for certain males. By looking at extreme values in distance and variability in distance traveled, we were able to determine patterns of birthing, migration, and social behaviors. So first I'm going to talk about birthing. In the literature, we found that around half to 2/3 of females give birth in a given year in May or June, July. And these females move less during birth and shortly after birth compared to other females. We looked at the daily distance traveled in 2019 for all females. Here's an example of one female and the distance traveled in a day throughout the year. When we focus on the reference period, I've highlighted in red the days where this female was moving much less than expected. So it's likely that she gave birth during this period. In order to define an algorithm to qualify what is meant by moving less, we compare all the females to the males. In this graph, we're showing the relative mobility during the reference period. So 0% means completely normal behavior, and 50% means during the reference period, I moved very little for at least 50% of the time. In pink, we're showing the females, and in blue, the males. So we decided to set a criteria, birthing threshold, and determined that females who move less than most of the males are considered to have probably given birth. We found 20 females who probably given birth. By using the kernel method, we calculated the likely birthing zone. For example, in Rachia, in dark green, the likely birthing zone within her entire home range. The second behavior we observed by studying distance was migration. So we define a simple migration by an individual having two zones, one winter zone and one summer zone. So in a typical year, we should observe presence in a winter zone, in a summer zone, and then back to the winter zone. We use the net squared displacement to measure this behavior. So in the case of starting at the winter zone, the net squared displacement would be equal to 0. And the net squared displacement is just the distance squared from an origin point. So arriving to the summer zone, all of a sudden the net squared displacement should increase. And then upon return to the winter zone, the net squared displacement should return to 0. So we should expect this type of graph. Winter zone, summer zone, winter zone. We calculate this parameter for all of our individuals and define statistical rules to determine whether or not the individual's behavior can be qualified as migratory or not. From the 83 ibex years, we found around half of these years are of the migratory type. So on the left, with an example of a typical migration pattern from January through to June at the winter zone, a sudden displacement to the summer zone, and then a return to the winter zone in mid-November. So another example which doesn't fit this migratory pattern is this individual, Benny, who, although appears to have a winter zone pretty stably in June, from the period June through to December, is showing several plateaus, so a likely presence of more than one zone used, some more complex behavior, and certainly no return back to the winter zone at the end of the year. So to investigate these type of non-classical simple migratory patterns, we created an algorithm to detect seasonal home ranges. So our algorithm allowed us to detect seasonal home ranges for most individuals. About half the individuals had two home ranges, winter, summer. but some individuals up to 5 separate home ranges. Here's an example of Joyeuse, where we've identified a summer home range in yellow and a winter home range in blue. Using this algorithm, we're also able to figure out all of the trajectory between home ranges. We're interested in these home ranges, and more specifically, the distance between them. But the distance between home ranges we found to be most often less than 5 kilometers, and very often less than 1 kilometer. So these different home ranges are in fact not very far apart, typically. We found surprising results with the timing of these migrations between home ranges. So in this graph, we show the number of migrations by month. And I want to focus on the dark blue color, which corresponds to migrations from a winter zone to a summer zone. We can see that these types of migrations occur all year long. We decided to divide this into migrations leading to long stays to short stays. So we defined the long stays as staying at the destination for at least 40 days. And again, focusing on the dark blue, we can see that these migrations from a winter zone to a summer zone mostly happen in April, May, June. When we look at short stays, leading to less than 5 days spent on the destination zone, we can see that these dark blue migrations occur all year long. So we concluded that a lot of individuals are moving from zone to zone, and this is happening all year long. The last idea I want to talk about is how we use distance to establish social networks. We define 2 relationship types based on distance: generally close individuals and occasionally close individuals. On the left, we have an example of 2 individuals who are generally close, which we define as having an average distance between them less than 1 kilometer. You can see that their data are quite often superimposed. On the right, an example of 2 groups of individuals who are occasionally close. So although their average distance between these individuals is 5 kilometers, at some point during the 500 days that they were observed in common, they were as close as 15 meters apart. So we present these individuals on a network graph. In this graph, each point is an ibex. The color and the shape tells us its character of origin and its sex. If individuals are generally close, they are linked in the graph. So what we can notice is more than half of the ibex are isolated, and among the groups that are created, they are all they're all within the same colony. When we look at the second network graph, we're showing individuals who are occasionally close. Again, meaning that at some point, they were less than 1 kilometer apart. This would give them an opportunity to transmit disease, to reproduce, for example. In this case, we find most individuals, 94%, are in proximity with at least one other individual during the observation period. In fact, we even have some really large networks formed. For example, this is from Parc des Écrins, which are linked in 2 places by males. So that's all I'm going to say about the analysis we've concluded. I would invite you to read our report. As a part of the project, we've made available all of the data, all of the methods used to treat the data, and there is in fact an online platform where you can play around and look at the data to look at all the maps that we've created in all the graphs. So with that, I'll take any questions.